Hello everyone. Now we've finished the midterm. I'd like to take this opportunity to review everything we've learned so far before we move to our new material. In today's video, we are not going to solve a lot of new questions. Instead, we're going to step back and connect the key ideas from chapter 1 through 7. The first goal is to review the main concept from each chapter and understand how they related to one another. Sometimes it's easy to focus on individual formulas, but statistics is really about knowing which tool to use in different situations. The second goal is to summarize the statistical tools that you should now feel comfortable using. By this point in the course, you've learned descriptive statistics, probabilities, distributions, normal distributions, confidence intervals, and several useful Excel functions. Rather than memorizing everything separately, I want you to see how these topics fit together. We also spend some time reflecting on the midterm instead of focusing only on your grades, thinking about what worked well during your preparation and where you can continue improving. Making mistakes is part of learning process, and understanding those mistakes is one of the best way to prepare for the final exam, which is very important. Finally, I'll explain how our tutorials will work for the remainder of the semester and introduce some new learning resources that will be available to help you to stay on track. So instead, let's begin by reviewing the foundation of statistics in chapter 1. Let's begin by reviewing chapter 1, which provides the foundation for everything we've learned in this course. Although this chapter doesn't contain many calculations, it's one of the most important chapters because it teaches us how to think like a statistician before jumping into formulas. Let's first look at the concepts on the left. One of the first ideas we learned was the differences between a population and a sample. A population refers to the entire group we were interested in studying, while a sample is only a subset of the population. For example, if we want to know the average GPA of all Sheridan students, every Sheridan student will be part of the population. However, if we survey only 300 students, so 300 students form our sample. This distinction is important because it determines which formulas we'll use later in the course. Next, we learn about the differences between a parameter and a statistic. A parameter is a value that describes a population, while a statistic describes a sample. For example, the true average GPA of all Sheridan students is a population parameter. The average GPA calculated from our survey of 300 students is a sample statistic. Later in the course, when we build confidence intervals, we'll use sample statistics to estimate unknown population parameters. We also introduce different types of data. Some variables are qualitative, meaning they describe categories rather than numerical values. Examples include major, eye color, or favorite sport. Other variables are quantitative, meaning they represent numerical measurements, such as height, weight, age, or exam scores. We also distinguish between discrete and continuous variables. Discrete variables are countable, such as the number of siblings or the number of students in a class. Continuous variable can take any value within a range, such as height, temperature, or time. Finally, we learn about the 4 levels of measurement: nominal, ordinal, interval, and ratio. These levels help us understand what kinds of statistical analyses are appropriate for different types of data. For example, with ratio data, meaningful comparisons and ratios can be made because there's a true 0. Height and weight are good examples. Now let's look at the section on right. I think this is one of the most useful habits you can develop throughout this course. Before calculating anything, pause for a few seconds and ask yourself these 4 questions. First, who or what is being studied? Second, am I working with a population or sample? Third, what type of variable am I dealing with? Finally, what level of measurement does this variable have? These questions may seem simple, but they help you choose the correct statistical method later on. Instead of memorizing formulas first, try to classify the problem correctly. Once you've done that, selecting the appropriate formula becomes much easier. And as the sentence, good analysis starts with good classification. That's exactly the mindset we'll continue using throughout the rest of the course. Now, let's move on to Chapter 2, where we learn how to organize and visualize data. At first glance, this chapter may seem fairly straightforward because there aren't any formulas to memorize. However, it's actually an important chapter because before we can analyze data, we first need to present it in a meaningful way. Let's first review the topic listed on the left. One of the first things we learned was how to construct frequency tables and relative frequency tables. A frequency table simply tells us how many observations fall into each category or interval, while a relative frequency table tells us the proportion or percentage of observations in each group. These tables help us summarize large data sets and make patterns much easier to identify. We also learned several important terms used when constructing group data. For example, class minutes tells us each class begins and ends. Class midpoints is the value halfway between the lower and upper class limits. Class wise is simply the difference between consecutive class boundaries or lower class limits. Understanding these definitions is important because they are frequently tested in quizzes and exams. Now we look at different types of graphs. Instead of trying to memorize every graph individually, I recommend thinking about the type of data you have. For categorical data such as favorite sport, a bar chart or pie chart is usually the most appropriate choice. For numerical data such as height or exam scores, we normally use the histogram because it shows the distribution of data across intervals. If we're interested in how data changes over time, such as monthly sales or daily temperatures, a time series graph is the best option. Finally, when we're studying the relationship between two quantitative variables, such as hours studied or exam scores, we use the scatter plot. Scatter plots are especially useful because they allow us to examine correlation and identify possible trends between variables. Now let's look at the section of the right. One of the most common mistakes people make is choosing a graph simply because it looks familiar. Instead, always ask yourself, what type of data am I working with? If it's categorical, choose a bar chart or pie chart. If it's continuous, choose a histogram. If it's time-based data, choose a time series graph. Once you've selected the correct graph, the next step is interpreting it. Rather than immediately looking for calculations, try to answer a few simple questions. What is the center of data? How much variation is there? Is the distribution symmetric or skewed? Are there any unusual values or possible outliers? These observations often tell us how much more than a single numerical summary. By the end of this chapter, you should be able to not only create appropriate graphs, but also explain what those graphs tell us about the data. Now let's move to chapter 3. This chapter includes many of the statistical measures that we will continue using throughout the rest of the course. Instead of simply organizing data, we are now trying to describe what the data is telling us. Many students feel overwhelmed by the number of formulas in this chapter. However, I encourage you not to memorize them one by one. Instead, organize them by purpose. Let's start with the first group of the measures. This includes the mean, median, mode, and mid-range. The mean or average is probably the measure you are most familiar with. It uses every observation in the dataset, making it a good overall summary when the data is fairly symmetric. The median is the middle value after arranging the data from smallest to largest. One important advantage of the median is that it is much less affected by extreme values or outliers. For example, imagine a company where one CEO earns several $1 million while everyone else earns around $50,000. This is very common in our life, right? In this case, the mean salary would be much higher than what the most employees actually earn. The median will provide a much better description of a typical employee salary. The mode is simply the value that occurs most frequently, while the mid-range is the average of the minimum and the maximum value. Although the mid-range is easy to calculate, it is very sensitive to outliers and is rarely used in practice. Next, let's look at the measure of variations, which tell us how spirited out the data are. The range is the simplest measure, is calculated by subtracting the smallest value from the largest value. However, because it's only used to observations, it can be greatly affected by outliers. The measure is the variance, which tells us how much the observations vary around the mean. The standard deviation is simply the square root of the variance, and because it has the same units as the original data, it is often easier to interpret. A small standard deviation means the data are clustered closely around the mean, while a larger SD includes greater variability. We also learned about quartiles, percentiles, and the interquartile range, or IQR. Quartiles divided the data into 4 equal parts, while percentiles divided the data into 100 equal parts. The IQR measures the spirit of the middle 50% of the data and is calculated as Q3 minus Q1. The IQR is particularly useful because it helps us identify potential outliers. Using the 1.5 times IQR rule, we calculate the lower and upper fences. Any observation outside these fences is considered a potential outlier. Another important concept included is the coefficient of variation, or CV. Unlike the SD, the CV allows us to compare variability between datasets that have different units or very different means. For example, if we're comparing investment returns or production measurements from two different processes, the CV often provides a more meaningful comparison than the SD alone. Finally, let's talk about the Excel function used. There are functions that you use frequently in assignment and practical work. Average calculate the mean. Median finds the middle value. STDEV.S calculate the sample standard deviation. Quartile.INC returns quartiles. Percentile.INC returns percentiles. One important reminder is to pay attention to whether questions is asking about a sample or population, because this determines which statistical formula or Excel function should be used. So now let's learn how to summarize and describe data. The next step is understanding uncertainty. Let's move to chapter 4, probability. I personally think this is one of the most interesting chapters in the course because many of topics we learn later, such as probability distribution or normal distribution, are built on those probability concepts. Let's first look at different types of probability. The first one is the classical one. This is the type of probability we're probably most familiar with. It applies when every outcome is equally likely. For example, if we roll a fair 6-sided dice, each member has the same chance of appearing. The second is the empirical probability instead of using theory. This one is based on the observation or historical data. For example, if it's rained on 12 out of the last 3 days, we could use that information to estimate probability of the rain tomorrow. The third part is the subjective probability, which is based on personal judgment or experience. This is common in business and finance when experts estimate future events that can be calculated exactly. Now let's review some important probability rules. One rule that students often forget is the complement rule. Whenever you see phrases like at least one or not, don't rush into calculating the probability directly. Instead, ask yourself, would it be easier to calculate the opposite event first? Very often the answer is yes. For example, instead of finding the probability of getting at least one success, it's usually much easier to calculate the probability of getting no successes and then subtract the result from one. Another rule is the additional rule. Whenever you read the word or, you should immediately think about addition. However, remember that if two events can happen at the same time, you need to subtract the overlap. Otherwise, you will count this outcome twice. Now let's look at the multiplication rule. When you see the word and, think about multiplication. If the events are independent, the probability of both events happening is simply the probability of the first event multiplied the probability of the second event. A good example would be flipping a coin twice. The result of the first flip doesn't affect the second flip, so the two events are independent. The next is the conditional probability. Whenever you see the word given, that's a very strong clue that you are dealing with conditional probability. The idea is that we already know one event has happened, so the probability of the second event changes because our sample space becomes smaller. One common mistake students make is using the wrong denominator, so always pay close attention to what comes after the word given. Finally, let's talk about independent and dependent events. Independent events do not influence each other. For example, rolling a dice twice. The dependent events do influence each other. For example, drawing cards from a deck without replacement. Understanding whether events are dependent or not independent is extremely important because it tells you about the probability rule you should use. Before we finish in the chapter, I'd like to share some tips that help many students. Instead of memorizing formulas, focus on recognizing keywords in the questions. If you see or, think addition. If you see and, simple multiplication. If you see given, think conditional probability. If you see at least one, think about using the complement rule first. Once you build this habit, probability questions become much easier to solve. Okay, let's move to chapter 5. where we learn about discrete probability distributions. This chapter is one that many students found challenging because there are several different distributions and they can seem very similar at first. I recommend asking yourself also one simple question. What kind of situation is this describing? Let's first see what is a discrete random variable. It's just simply a variable that can only take certain countable values. For example, the number of students in a classroom, the number of defective products in a shipment, or the number of heads when flipping a coin several times. These are all countable outcomes, which means they are discrete. Next, we learn about probability distributions. It tells us all possible values that a random variable can take, along with the probability of each value occurring. We introduce two important concepts, expected value and variance. The expected value represents the long-run average outcome if an experiment is repeated many times. For example, if you repeatedly play the same game thousands of times, the average result will approach the expected value. Variance, on the other hand, tells us how spread out those outcomes are around the expected value. Now let's look at different distributions introduced in this chapter. The first and probably the most important and common one is the binomial distribution. Before using a binomial distribution, I always recommend checking four conditions. First, is there a fixed number of chairs? Second, does each chair have only two possible outcomes, such as success or failure? Third, are the chairs independent of each other? And finally, is the probability of success the same for every chair? If all four conditions are satisfied, then you're probably dealing with a binomial distribution. For example, flipping a coin 10 times and counting the number of heads would be a classic binomial problem. The next distribution is the Poisson distribution. Unlike the binomial one, Poisson is used when we are counting how many times an event occurs during a fixed interval of time, distance, or area. For example, the number of customers entering a store in 1 hour, or the number of emails received one day. Whenever you see the word like per hour, per minute, or per kilometer, Poisson is often a good model to consider. We also learned the dramatic distribution. The key here is that we're interested in the first success. For example, how many times do we need to flip a coin before getting the first head? Notice that we're no longer counting the total number of success. Instead, we're asking how long it takes until the first success occurs. Finally, we introduce the hypergeometric distribution. This distribution is similar to the binomial one, but there's one important difference. We are sampling without replacement. Because we're not replacing the selected items, the probability changes after each selection, meaning the chairs are no longer independent. This is usually the easiest way to distinguish this one from binomial. Before finishing this chapter, I'd like to share some study tips. Many students spend a lot of time memorizing formulas, but I think spending more time learning when to use each distribution is more important. During exam, the biggest challenge usually isn't the calculation itself, it's identifying the correct model. If you can correctly identify the distribution, most of the calculation become much more straightforward. Okay, now let's move to chapter 6, the normal distribution. Many of questions on midterm came from this chapter, and it's also a chapter that we'll continue building on later in this course. The good news is that once you understand the logic behind the normal distribution, most questions follow the same pattern. Let's first look at the differences distribution we introduced. The first one is the uniform distribution. It just simply means that at every value within a given interval is equally likely to occur. For example, if a random variable is uniformly distributed between 0 and 10, then every number between 0 and 10 has the same chance of being selected. Compared with normal distribution, the uniform distribution is much simpler because the probability density is constant across the entire interval. The normal distribution is one of the most commonly used distributions because many real-world measurements approximately follow this pattern. Examples include exam scores, height, weight, and many biological measurements. One important characteristic of the normal distribution is that it's symmetric around the mean. The means, the left side and the right side are mirror images of each other. The highest point of the curve is located at the mean, and as we move further away from the mean, the probability gradually decreases. To answer probability questions involving in the normal distribution, we introduce the z-score. A z-score tells us how many standard deviation a particular value is above or below the mean. For example, if a student's score is exactly equal to the mean, the z-score is 0. If the score is 1 standard deviation above the mean, then the z-score is positive 1. Converting values into z-score allows us to compare observations from different nominal distributions using the same standard scale. Another area where many students lose marks was using the correct Excel function. If the question asks for a probability or an area under the curves, you should use the norm point dist. For example, if the question asks, what is the probability that a student's score is less than 80? You are looking for area, so normal point dist is the correct function. On the other hand, if the question gives you a percentile or probability, they ask you to find the corresponding value, then you should use the norm point INV. For example, if a question asks for scores corresponding to the 90th percentile, as you are looking for a value, the norm point INV is the correct choice. Another common mistake involves identifying which part of the curve you need. If the question asks for the probability or being less than a value, then you are looking for the left tail. If it asks for the probability of being greater than a value, remember that Excel gives you the left tail probability by default, so you will need to subtract the result from 1. If the question asks about for probability of being between two values, calculate the cumulative probability for the upper value first, then subtract the cumulative probability from the lower value. Many students know the correct Excel function but lose marks because they forget the final subtraction. Finally, toward the end of chapter, we introduce the sampling distribution of the sample mean. This idea is extremely important because it prepares us for confidence interval in the next chapter. Instead of looking at individual observation, we are now looking at sample means. The key difference is that the variability becomes smaller because we use standard error rather than the original standard deviation. If there's something I'd like you to remember from this chapter, is don't memorize every situation separately. Instead, ask yourself, am I looking for a probability or value? Which region of the normal curve does the question describe? If you answer these two questions correctly, choosing the right Excel function becomes much easier, and the most nominal distribution problems become very manageable. Okay, now let's move to the chapter 7, which introduces one of the most practical topics in the statistics, confidence interval. Up until this point in the course, we've learned how to summarize data and calculate probabilities. Now we are going to one step further. Instead of simply describing a sample, we are using this sample to make conclusions about the entire population. That's really what statistics are all about. The first concept we learn is the differences between a point estimate and an interval estimate. A point estimate is a single value that we use to estimate an unknown population parameter. For example, if we survey 100 students and calculate an average exam score of 76, then 76 is our point estimate. However, because we're only using a sample rather than the entire population, we know that the population is unlikely to be exactly 76. This is why we are using our interval estimate, or a confidence interval. Instead of giving just one number, we provide a range of values that are unlikely to contain the true population parameter. Next, let's introduce the concept of a confidence interval. You usually see confidence levels such as 90%, 95%. One very common misunderstanding is the interpretation of a confidence interval. For example, suppose we calculate a 95 confidence interval. This does not mean that there is a 95% chance that the true population mean is inside this interval. Instead, it means that if we repeatedly collected many random samples and constructed confidence interval using the same method, about 95 of those intervals will contain the true population parameter. It's subtle differences, but it's one of the most frequently tested concepts in statistics. Another important idea is the margin of error. The margin of error tells us how far we move above and below our sample estimate to create the CI. A larger margin of error gives us a wider interval, while a smaller one gives us a narrow interval. Several factors influence that. For example, increasing the sample size generally reduce the margin of error because larger samples provide more precise estimates. We also discussed when to use C procedures and when to use T procedures. If a population standard deviation is known, we generally use the C distribution. But if it's unknown, which is much more common in real life, we use the T distribution. Finally, we learn how to determine the minimum required sample size. One important reminder is that whenever you calculate the minimum sample size, you should always round up to the next whole number. Rounding down would give you fewer observations than required and could reduce the accuracy of your estimate. Before we finish in this chapter, I'd like to leave you some key takeaway. Always ask yourself, what am I estimating? How confident do I want to be? And how should I interpret the final intervals? Now we've reviewed all the 7 chapters. Let's take a quick look at Excel function that you'll be using for this course. So as I mentioned before, the functions are mainly used to describe and summarize data. For example, we're looking for the average, we use the average. If we're looking for the middle value, we use the median. To measure the variability, we use the S, TDEV point S or var S. So those functions I listed here are like the most commonly used functions in Excel. and just ensure you know all the meaning of it and how to use it properly. I'm gonna upload this PPT later, so you can find this page in the PPT. And now we finish reviewing the contents. I'd like to spend a few minutes talking about the midterm. Whether you were happy with the result or not, I think it's important to remember that the midterm is only one part of the course. Instead of asking yourself what grade did you get, try asking different questions. What did I learn from this experience? Very often, that's much more valuable. When I worked with students during tutoring sessions, I noticed that many mistakes are not caused by difficult calculations. Instead, they are caused by small decisions made before the calculation even begins. For example, choosing the wrong distribution, using the wrong Excel functions, misreading what the question is asking, or forgetting to interpret the final answer. That's why I'd like to introduce this simple six-step checklist. So, step 1, identify the variable and parameter. Before touching your calculator Excel, ask yourself, what exactly am I trying to find? Is this a probability, a mean, a confidence interval, or something else? Step 2, choose the correct model or distribution. Do I need a binomial distribution, a Poisson distribution, a normal distribution, or is this simply a descriptive statistic problem? Step 3 is judge the situation whenever possible. For probability questions, drawing a quick picture or writing down the event can make the questions much easier to understand. For normal distribution questions, I always recommend drawing a simple normal curve and shading the regions you are trying to calculate. Even a rough sketch can help you avoid many common mistakes. Step 4. Perform the calculation carefully. Whether you are using your calculation or Excel, make sure you enter the correct values and your units make sense. For example, don't accidentally mix percentage with decimals or sample standard deviation with population standard deviations. These small details can make a big difference. Step 5. Check whether your answer is reasonable. Ask yourself, does the probability make sense? Can a probability be greater than 1? Does the confidence interval seem realistic? Developing these habits only take a few seconds, but it can help you catch simple mistakes before submitting work. Finally, interpret your answer. In statistics, the calculation is the only part of solution. You should also be able to explain what your result means in the context of the problem. If there's one message I'd like you to take away from today's review, is this: try to spend less time memorizing formulas and more time to understanding the reason behind each question. Statistics becomes much easier when you're focusing on thinking through problems rather than simply searching for the next formula to apply. Now we reflected on the midterm and discussed some strategies for improving. I'd like to finish by talking about what you can expect from the rest of the semester and the resources that were available to support your learning. Before finishing today's review, I'd like to share that you can expect for the rest of semester. Starting next week, I'll posting weekly tutorial video on Slate. These videos are designed to support what you are learning in class and provide another opportunity to review the materials at your own pace. Each week, I'll summarize the key concepts covered in the lecture, review important formulas, walk through worked examples, and highlight some of the common mistakes that students often make. My goal is to help you build confidence with materials before quizzes, assignments, and eventually the final exam. I also encourage you to watch the tutorial before coming to the tutorial session. If possible, that way you will already have an overview of the weekly content and you can use the tutorial to ask questions. clarify difficult concepts, and work through problems that you found challenging. Remember, tutorials are most effective when you come with specific questions, whether it is sometimes from the lecture, the homework, or the tutorial video. As we move to the second half of the semester, we'll continue building on the foundation we've established in the first 7 chapters. Many of these upcoming topics are connected to what we've learned. So having a solid understanding of these concepts will make the rest of the courses much easier. Finally, I'd like to thank you for taking the time to watch this video. I hope it helped you organize what we've learned so far and give you a clear picture of how different topics connected with each other. I wish you all best for the rest of the semester. Keep practicing, stay curious, and remember that learning statistics is a process. Don't be discouraged if some topics feel difficult at first. Confidence comes with practice. And for our weekly tutorial, we're just gonna have simple question and answer parts. If you have any question, you are welcome to come to my session and also book some one-on-one session with me. My name is Lucienne Zhang, and you can find me in the tutorial. Thanks again for watching, and I look forward to seeing you in the future tutorials and in the weekly video on Slate. Take care and have a wonderful rest of your semester.